Okay, ladies and gentlemen, so let's see where we're at on our little procedure here. Curve sketching procedures. We've taken a look at domain, we've done intercepts, we've looked at symmetry, we've done the asymptotes with limits. We're now on some interesting stuff called determining the intervals of increase or decrease. We're going to do that using the first derivative. We're going to find areas where the curve can change from increasing to decreasing, or vice versa. We're going to set up an interval chart, and then we're going to determine any max or minimum points, local max or minimum points that might exist, and then we're going to know a little bit more about this curve. So let's start off, and I'll show you how this works. So we start off, first of all, we're going to need a derivative now. Okay, so our first curve, what we're sketching, was given by. Now, off camera, I went and did this. I don't want you sitting through more videos than you need to, and that was definitely done off camera. But it is certainly something that you have to be able to do, okay? You have to be able to get the derivative right, and if you don't, then everything else from here is going to fall apart. I can't tell you the number of times that's happened to me, and it just happens. You got to be careful. Okay, so what we want to do is we want to determine where f of x can, now it doesn't mean that it necessarily has to, but can change from increasing to decreasing, or vice versa. Oh, by the way, these are called intervals of increase and decrease. And it's characteristic 5 that we're looking at. Okay, so, and we've talked yesterday about, or today's in class, we talked about when that can happen. And we know that f of x is increasing if f of x is greater than 0, prime, sorry. And we know that f of x is decreasing if f prime of x is less than 0. Therefore, if I'm going to change from increasing to decreasing, that's going to occur. Any changes occur when f prime of x equals 0 and when f of x is undefined at a vertical asymptote per se. So, taking a look at this, what we'll do is we'll take our first derivative and we'll set it equal to 0. I like to look at that and think of a little indivisible 1 down there, and so it's going to be cross multiply, and so we come up with x equals 1. That means that our curve can change from increasing to decreasing, or decreasing to increasing at x equals 1, because the derivative at x equals 1 is horizontal. Okay, so it goes through that point. F prime, when is it going to be undefined? Well, f prime is undefined when x plus 1 to the 3 is equal to 0. So when we're dividing this by 0, and that's a problem. Cubed root both sides, and x equals negative 1. So also our curve can change from increasing to decreasing at x equals negative 1. We call these the first derivative critical values. Plus and negative 1. What that means is, now let's make sure that we understand what's going on here, is that if I have a Cartesian plane, then I know that out here at negative 1 and out here at 1, these are places where, I'm going to zoom in a little bit, these are places where it can change from increasing to decreasing or decreasing to increasing. So that means they can't change anywhere else. Okay? So whatever it is from here, x less than negative 1, it has to stay until this point, which is our vertical asymptote. In which case it can change if it wants to, but whatever it changes to right after -1, it needs to stay the same. I'm going to try focusing for you. It has to stay the same all the way in there. So whatever it is, it's got to stay the same. Then it has another chance to change. Doesn't mean that it has to, but it can change here. Now your intervals look like this. That's how we do it with the alligator notation, if you will. I'm lacking the language that I need right now. So these are our intervals. There's another way to talk about these intervals, just because I'm going to use it in a little bit. Way out here is negative infinity. So we could talk about this interval as negative infinity up to -1. Not including that, and certainly not including negative infinity. That's why we use round brackets. If we wanted to include the endpoints, they'd be square brackets. So this one would be -1 to 1, and this one will be 1 to infinity. And that's just another way to talk about this notation. So this notation is exactly mirrored in this notation. But you got to be careful, right? Because these look like points. So we got to know what we're dealing with. Okay, so we've got our critical values. We know where it can change. What's important now is our interval chart. So, interval chart. Now you have experience with interval charts, but your experience tells you when it's going to be above 0 or below 0. This is not that interval chart. This interval chart, first of all, let's set up our intervals. Okay. This interval chart needs to tell us something about the sign of the second derivative. Now the first derivative. The first derivative is given by 1 minus x over top of x plus 1 all to the 3. I want to know about this sign. So what I'm going to do is I'm going to take whatever it is that's going to contribute to the overall sign of f prime, and I'm going to put that in columns. And the first one is obviously the top, and the next one. And these guys, the sign of this and the sign of this, will tell me something about the sign of this. And that's what I'm interested in, the sign. Okay? So these guys are going to tell me about the sign of that. Let's see how that works. So if I choose a value that's less than -1, like -5, it'll be 1, -5, and that'll be positive. If I put in a value between -1 and 1, like 0, then it's 1 minus 0, and that'll be positive. If I put in a value greater than 1, like 18, it'll be 1 minus 18, which will be negative. It's cubic, so I have to worry about it. If it was even, then whatever this was would become positive, and I just put positives down here. But it's not. So if I'm less than -1, like -2, it'll be -2 plus 1 is -1. -1 cubed is negative. Put in 0, it's convenient. It's going to be positive. Put in 2. It'll be 3, 3 cubed. Don't care what it is, other than that it's positive. This sign of the top, this sign of the bottom, will give an overall sign of negative, which means that f prime of x is less than 0. This one will be positive. This one will be negative. So what that tells me is it tells me something about f of x. If the first derivative is less than 0, then f of x is decreasing on -infinity to -1, that entire interval. If f prime of x is positive, then it's increasing on -1 to 1. And if it's f prime is negative, then it will be decreasing on 1 to infinity. Infinity and beyond. There's my interval chart. Okay, so when we were talking back here, we know now that we've got f, well, why don't I do a little bit of a just quick little chart. you won't have to do this on your test necessarily, but it gives you an idea of what's going on. You've got this point -1 here. You've got this point 1 here. And on your intervals, for this entire interval, f prime of x is less than 0. On this entire interval, f prime of x is greater than 0. This entire interval, f prime of x is less than 0, which means that the curve is decreasing here. The curve is increasing here. And the curve is decreasing there and beyond. Now what's interesting is we know that this is a vertical asymptote. Okay, so we get what's happening there. But look here, this is kind of cool. It's changing from increasing to decreasing right there. So it's going from increasing to decreasing. Increasing to decreasing. Meaning, right there is a local maximum at x equals 1, where that crosses over. And that local maximum, okay, what local maximum means is that that point is higher than the points on either side of it, directly on either side. Okay, so to be a local maximum, you have to have points on either side. That's going to be important later. You have to have points on either side to be a local maximum. And you have to be higher. So increasing to decreasing. Now that exact point, if I wanted to figure that out on the curve, and we're going to want to do that, so local max at 1 comma f of 1, not f prime of 1, but f of 1 back to the original. So it's going to be 1 over 1 plus 1 squared. So that's going to be 1 1/4. Now, here, we have the same sort of interesting thing happening here. I go from decreasing to increasing. So you would think that I've got something happening like this. I'm going from decreasing to increasing at this -1 spot. But if I go and try to say that this is a local minimum, if I go and try to say that, look what's going to happen. -1, f of -1, -1, and you're going to get -1 over top of -1 plus 1, is that right? Yep. Which is -1 comma -1 over 0. And this is undefined. So in case you didn't remember, it's going to become blatantly obvious when you go to try to find that y value that this cannot be a local minimum because there is a vertical asymptote at x equals -1. So there is no local minimum here. That's your vertical asymptote. But this was a local maximum. Okay? So that's pretty good. We can finish that, and then we'll take a look at the second derivative, and we'll be dealing with concavity.